Okay, welcome. So when I returned from summer break in the fall, my students were asking me about the Oppenheimer movie, and they also asked me if I would show the movie to them in class, and I said yes if you'll let me teach you a couple of chapters of nuclear physics, and they agreed. So I taught that to them, and I think they enjoyed it, and I decided that maybe other physics students would enjoy it as well. So I summarized some of my notes and I put it into a video, and that's what this is. I will start with a relevant clip from the movie. Okay, in terms of nuclear physics, this looks like it's maybe one of the most important parts of the movie. The first equation looks like the Coulomb energy equation. The second equation looks like the nuclear force energy. The third item on the board looks like the condition for the Coulomb energy to exceed the nuclear force energy, which induces the fission. The fourth item on the board looks like the assumption that the uranium nucleus can be approximated as a sphere. Nuclear physics basics. Okay, so a lot of this you probably already know. The nucleus is composed of neutrons and protons. Protons and neutrons are called nucleons. Neutrons are neutrally charged and protons are positively charged. There are two forces which act on the neutrons and protons inside the nucleus. The Coulomb force, which is the force that causes like charges to repel and opposite charges to attract. And this force is stronger the closer the particles are. The strong nuclear force, which provides an attractive force between neutrons and neutrons, neutrons and protons, and protons and protons. This is a very short acting force that acts inside the nucleus. It's actually a lot stronger than the Coulomb force, but again, very short acting. So the Coulomb force wants to blow the nucleus apart, right? Because the protons are repelling the protons, and the neutrons are neutrally charged, and the strong nuclear force wants to keep it together. Thankfully, the strong nuclear force is much stronger, as I mentioned before, than the Coulomb force. Where does the power of the fission bomb come from? Well, it comes from the release of the binding energy in the nucleus. The binding energy of the nucleus comes from an exploded star. Atoms above iron exist due to fusion that can only occur in an exploding star. Nuclear theory. 1 plus 1 is greater than 2. You're probably saying, what? Well, for a deuterium nucleus made of 1 neutron and 1 proton, the sum of the masses of each does not equal the mass of the combined, which is the mass of the nucleus. So what happened to the mass? The mass was converted into energy that binds the proton and neutron together. Here are the numbers. Mass of a proton plus mass of a neutron does not equal to the mass of the nucleus. Okay, here's the proof. Here's the mass of a proton in mega electron volts. The mass of a neutron, okay, total 1878 mega electron volts. If we actually weigh the deuterium nucleus through some other means, we had 1875. So 3 mega electron volts was lost, and that was used. Or actually, where is that energy? It's in the energy required to bind the neutron and the proton in this example. Okay, so this is just a neutron and a proton in a very simple hydrogen deuterium atom. But say we fuse 2 hydrogen atoms into a helium atom. Okay, so it's the same idea. The mass of the helium atom is less than the sum of the masses of the hydrogen atom, again, because some of the energy is in the binding of the hydrogen nuclei. The general equation for computing binding energy of a nucleus, okay, so this would be the nucleus X, say helium, for example. So A is the number of neutrons plus the number of protons. Z is the number of protons. Okay, so how do we compute the binding energy for this atom? Well, we're going to multiply the mass of the neutron okay, by the number of neutrons. We're going to add to that the number of protons times the mass of a proton. So that's just a hydrogen nucleus, right? Hydrogen nucleus, not deuterium, but the other isotope, has just one proton, okay? And then we're going to subtract the mass of the nucleus of this atom of interest, okay? We'll then multiply that by c squared, and that will give us the binding energy. Nuclear binding energy for atoms above iron, uranium, for example, which we'll deal with in this presentation, and also which was the atom used in the first nuclear fission bomb. Okay, so the binding energy comes from an exploded star, at least for uranium. For elements in the periodic table below iron, you just need a star in its later stages that can fuse elements lower in the periodic table to elements higher in the periodic table. But once again, for uranium, you need the pressure of a supernova. Okay, so right here is the nuclear equation relevant in the movie Oppenheimer and that of the first bomb dropped in Japan by the United States. Okay, so this is a bombarding slow neutron. Okay, so you're going to take a supply of neutrons and you're going to send them towards a uranium-235 atom. Okay, 92 protons, combined neutrons and protons 235. That's going to induce fission. And what you get is the end products of barium and krypton and 3 neutrons. Okay, there's actually an intermediate step. Okay, so this will, upon capturing the neutron, uranium-235 will turn into uranium-236. Okay, this bombarding neutron will cause deformity of uranium-235. It will cause it to stretch and vibrate. Okay, as a result of this, the strong nuclear force drops by an amount greater than the repulsive Coulomb force, which is the proton to proton repulsive force. And as a result, it'll cause uranium-236 to split into the barium and krypton atoms and also the 3 neutrons. Okay, a little bit more about the end products. So barium-141 is produced, and also krypton-92 is produced. And again, here are the 3 neutrons that are also coming out of this reaction. This is important because if you have a large number of uranium-235 atoms, these neutrons, which come out of this reaction, can induce fission in other atoms of the sample. Okay, so 170 mega electron volts. Okay, is that a lot of energy? So it's really not, but it's only one atom of uranium that this pertains to. Okay, so converting mega electron volts to joules, which is something we're all more familiar with, you get 2.7237 times 10 to the minus 11th joules. Okay, so that's a tiny, tiny bit. So how much energy would be released in 1/2 pound of uranium? Well, it's immense. Okay. It would be 1.6 times 10 to the 13th joules. Okay, so the fission of uranium-235 could occur on its own without bombarding it with a slow neutron, but it would take a very long time. So you can see from this table, it would take about 700 million years for one half of uranium-235 to decay into the barium and krypton. Okay, so to compute the energy of this nuclear reaction, it's pretty straightforward to compute the rest energy of the neutron and the uranium atom, and then also the energy of the products, the barium and the krypton and the 3 neutrons. And we're going to use E is equal to mc squared to do that. So again, nuclear physicists work in mass of atomic mass units, and 1 atomic mass unit multiplied by c squared is 931.5 mega electron volts. Okay, right here. That also happens to be 0.9315 giga electron volts. Okay, 10 to the 6 mega electron volts. Okay, 10 to the 6 is mega, 10 to the 9th is giga. Okay, so I'm going to work with giga here. Okay, so it's pretty simple. Working with atomic mass units, because that's 235 is approximately the atomic mass units of uranium, right? It's the atomic mass number, which is the number of protons plus the number of neutrons. Okay, so the rest energy of a neutron, 1 atomic mass unit times c squared, is 0.931 giga electron volts. The rest energy of uranium-235 is slightly more than 235, 235.04. And again, multiplying that by UC squared, where 1 UC squared is this, it gives me 219 giga electron volts. Rest energy of barium is 131 giga electron volts. Rest energy of krypton, 92 is 86, etc. Okay, so now I just add up the energy of the neutron and the uranium rest energies, and I'm going to subtract the rest energies of the barium, krypton, and the 3 neutrons to get 1.7 giga electron volts, which is 170 mega electron volts. Okay, so let me show you a simulation of this reaction. Okay, so I'm going to shoot a neutron from this apparatus towards a uranium-235 nucleus, and that should induce fission. So you can see the vibration causes deformity of the uranium-235 nucleus. So the deformity of the shape reduces the strong nuclear force by an amount greater than the drop in the Coulomb repulsion force between the protons, and that causes it to split into the 2 daughter nuclei here. Okay, so as I mentioned in the nuclear reaction, when uranium-235 fissions into krypton and barium, it also gives off 3 neutrons. Okay, this is critical. If it didn't give off those 3 neutrons, there would be no chain reaction, no nuclear reactors, and no fission bombs. Okay, here is a simulation. As the mass of the nuclei increases, the nucleus becomes unstable. It wants to spontaneously break apart. Okay. And the larger it is, the shorter the half-life. So in this figure, on this axis, I've got the number of neutrons, and on this axis, I've got the number of protons. And this black line right here are stable nuclei. Okay. Okay, so let's take a look at this. Okay, so there are several important facts we can extract from this figure. First, it appears that for the sum of neutrons and protons less than 40, so the sum less than 40, so right in this area, nature prefers the number of protons and neutrons in the nucleus to be the same. So, right, you can see this, these dark lines right here line up with the straight line. The straight line is number of neutrons is equal to the number of protons. Okay, so that makes sense. But as the mass of the nucleus increases, in other words, more neutrons and protons, the more that nature favors a higher ratio of neutrons to protons. Okay. So if you pick a point here, okay, this would be stable. Okay, you see the dark black line here. Okay, so this would have 82 protons and far more numbers of neutrons. Okay, This would not be stable. So 82 protons and 82 neutrons, okay, for larger mass nuclei, you don't see them, right? Okay, so why does this make sense? In the case of an added neutron, okay, the higher number of neutrons contributes to greater nuclear force and the nuclear binding energy, while not contributing to the repulsive electric force. Okay, so add neutrons, not a problem, right? So that's why you're seeing uh, more neutrons here than protons as this thing gets larger. But adding one proton, right, Z, um, to the nucleus adds only 1 unit of nuclear binding energy, right? Because protons will be attracted to protons via the nuclear binding energy, but the repulsive Coulomb energy increases by 2Z, okay? And I'll show you the equation that will prove that. So eventually, as more protons are added, the repulsive force of the Coulomb force, okay, protons repelling protons, exceeds the attractive strong nuclear force, and the nucleus breaks into smaller, more stable nuclei. The figure also reveals that there are no stable nuclei with Z greater than 83. Okay, so to the right of the red line, there are no stable nuclei. And also for A greater than 209. Okay, A is the total number of neutrons and protons. Okay, so so in this territory, so even at Z equal 83, right, is the number of neutrons, goes up, you still don't have stable nuclei. Okay, some additional details. Why do some atoms fission spontaneously with minimal activation energy? Okay. Okay, this comes from Richard Feynman's Volume 1 Lectures on Physics. He proposes this as an equation for the strong nuclear force. He doesn't know, or nobody knows precisely what that equation is, but Feynman argues that it looks something like this. Okay, this is probably a key component of it. We know this from experiments. So I graphed this, and it looks like this. Okay, so this makes sense, right? We're finding from experiments is as the radius of the nuclei increases, right? So you're moving along this axis, the nuclear force drops. Okay. The radius of the nucleus is a function of the number of nuclei. Okay. So this is a constant estimated to be 1.2 times 10 to the minus 15th. Okay. So as you add neutrons and protons, this gets larger. As this gets larger, the strong nuclear force gets smaller. Okay. So it's all making perfect sense. The larger the mass, the less the strong nuclear force, which keeps the nucleus together. And the Coulomb force also drops off some, but not as much as the strong nuclear force. Okay, so the Coulomb force drives the protons apart from each other. Here is a useful expression. The Coulomb force energy required to keep a sphere of protons within a sphere of radius r. Okay, so a sphere is a decent approximation for the shape of a nucleus. Okay, so that energy is given by this expression, and it tells us that the larger Z, or the larger number of protons, the greater the energy required to keep the thing together. With a little calculus, we can see that dE is proportional to 2Z, so add a single proton and double the energy. So where does the power of the fission bomb come from? Okay, releasing the binding energy in the nucleus, as I said before. So any nucleus can be busted apart with enough energy of a bombarding particle. Okay, so let's get that straight. It doesn't have to be unstable, okay, like uranium-235. But if the energy of the bombarding particle exceeds the energy released upon the fission, okay, I meant fission here, not fusion, then there is no energy profit, right? Bombs don't go off, nuclear reactors don't produce power, and somebody pays the bill to accelerate the bombarding particle. Okay, So the key then is to find the atom, okay, that is inexpensive to bust apart. Okay. Now the fission barrier is the energy required to bust a nucleus apart. Okay. And you want that to be as small as possible. Okay. So as you might imagine, um, it goes up for a while. Okay, because the larger the atom to some point, right? The greater the nuclear force. The more stuff, the greater the forces. But again, as you start adding more and more, the thing gets larger and larger, right? And that strong nuclear force starts to drop off at a rate greater than that of the Coulomb force, which is trying to tear it apart. And eventually, right, the fission barrier, okay, the activation energy becomes really, really low. And for uranium 235, which is right about in here, it's like 6 mega electron volts. Okay. And I showed you before, okay, it only takes 6 mega electron volts of energy to get that neutron, the bombarding neutron, to sufficient speed to bust this thing apart. And yet, after the uranium 235 nucleus is busted apart, it gives off 170 mega electron volts. Okay, so if you subtract 6 mega electron volts from 170 mega electron volts, that's a huge energy profit. The other benefit of the uranium 235 reaction, as you saw in the nuclear equation, is that it produces more neutrons than that which go into it. So per one atom of uranium 235, it took one neutron, right, to induce the fission, and it gave off the two products plus three neutrons. Okay, and those three neutrons can be used to induce fission in other uranium atoms in the sample. Okay, part 2 of this video, more detailed yet complicated explanation. But getting into some really interesting topics, quantum tunneling, that which explains spontaneous decay, spontaneous fission, strong nuclear force, the liquid drop model, which is an approximation model for the strong nuclear force, and then also the computation of a nuclear stability model from the strong nuclear force liquid drop model. Quantum tunneling, extremely spooky but relevant to nuclear physics and the Oppenheimer movie. It is like a skateboarder rising to a height above where he started, with no outside force. This is a depiction of an alpha decay of uranium 235 to an alpha particle, which is a helium nucleus, and a thorium nucleus. This happens spontaneously due to quantum tunneling, and it takes over 700 million years for half of a sample of uranium 235 to decay. Uranium 235 decayed immediately upon the bombardment of a neutron, however, in the first nuclear bomb, depicted in the movie Oppenheimer and presented in this video. Another isotope of uranium, uranium 239, spontaneously decays in less than a second. So uranium 239 wouldn't be such good fissile material for an atomic bomb. It wouldn't last long enough for one to use it as a weapon. An analogy for quantum tunneling would be the skateboarder all of a sudden reaching a height above the initial starting point. So all of a sudden just going all the way to the top and flying off the ramp. Or a microscopic particle traveling through a barrier wall above the energy of its own. Realize atomic particles are modeled as waves, but when detected appear to be particles. We don't really understand the phenomena, but our models seem to work. Okay, so this is a particle. The energy of this barrier is lower than the energy of this particle. So the probability is good that it penetrates this wall. Okay. The area under this curve here is the probability. Okay, here is another barrier with an energy higher than that of this particle. So the probability is actually very low that it penetrates this energy barrier. And again, you can see that because very little of the wave went to the other side. So the probability is that this particle will be reflected from this wall, but there is some probability it makes it to the other side. So that's what quantum tunneling is about. When a uranium nuclei is struck by a slow neutron, which is what happens in a nuclear fission bomb, it obtains sufficient energy to rise above the energy barrier depicted to the left here. Here's the energy barrier. And as a result, the uranium-235 nuclei will break apart and release a lot of energy. But spontaneous decay, as presented on the previous slide, is due to luck, aka quantum tunneling. And as suggested on the previous slide, it takes 700 million years for only 1/2 of a sample of uranium-235 to do this. The spontaneous decay is also predicted by the quantum mechanics equations. The physics model that is used to predict how certain nuclei spontaneously decay via quantum tunneling is called the Schrodinger wave equation. This equation right here. The equation was created by Edwin Schrodinger. It is simply the mathematical model that fit the experimental results from an experiment called the double slit experiment. Schrodinger's equation is a fundamental law of the universe. In fact, Newton's laws of motion can be derived from Schrodinger's wave equation. So Schrodinger's equations are more fundamental than Newton's equations. It has predicted the results of countless subatomic phenomena, so we have great confidence in it. But we don't understand it at all. It implies dual nature of products, waves, and particles at the same time, quantum entanglement, which is interaction between particles that are light years apart, spontaneous alpha decay via miraculous quantum tunneling. And yes, this crazy equation is about probability of finding a particle at a particular location, say the probability of some velocity and or the probability of some energy, among other things. Okay, so these equations represent Schrodinger's equations at the three boundaries. Okay, this is region 1, incident wave or incident particle. This is region 2 inside this box, and region 3 is over here. All that is needed to solve these equations is the energy of the particle, E, the size of this energy barrier, V sub 0, and numerical value for L, the length of this barrier. The resulting solved equations can then be used to derive the equations on the next page, which can be used to compute the probability of the particle being located in any of the regions 1, 2, and 3. For the quantum tunneling problem, we're interested in the potential barrier, which is higher than the energy of the particle. The second wall here. Okay, so the equations here are the solutions to this differential Schrodinger wave equation for the three different regions. These differential equations can be solved by any math or physics major. It's fairly straightforward. They're linear differential equations. Okay, but these have constants in them. So we need the constants A, B, C, D, F, G, and K. The way we get those constants is from the initial conditions of the energy of the particle, the energy of the barrier, and also the length of the barrier. It turns out that for quantum tunneling, the only equations we're interested in is the A component of this equation, because that's in the direction of positive x. And we are also interested in the transmitted part of the equation incident on this wall. Okay, so the only equations, therefore, we're interested in include this equation and this equation. So the next thing I do is I use the initial conditions, the energy of the particle, the energy of the potential barrier, and the length of the barrier to go from this equation to this equation. And this equation will give me the probability of the particle tunneling through this barrier wall. Okay, so for spontaneous fission, the potential barrier which enslaves the alpha particle within the uranium-235 atom is this yellow line right here. So it is this barrier that the alpha particle must tunnel through to spontaneously fission from the uranium-235 atom. I will use the mathematical solution to the square root potential derived on previous pages to estimate the probability of the tunneling of the alpha particle through the blue box. Okay, from here through the blue box, which is an estimate or approximation to this Coulomb potential. Okay, so again, this is going to be simpler to deal with. I can use the equations on the previous page to compute the probability of tunneling through this versus this, but again, it'll be a fair approximation. Okay, so next I'm going to compute the probability of the alpha particle breaking away from the nucleus via the path shown by the purple line. Okay, so here is the barrier which it must penetrate. And again, it doesn't have enough energy to come over it like this. So via quantum tunneling, it's going to tunnel through like this. Okay, so first I compute the upper barrier here. Okay, so at this point, the nuclear force and energy and the Coulomb force and energy are equal. Okay, so the alpha particle is bound inside the nucleus since its energy is less than this, top of the barrier. Okay, this is the equation for the Coulomb energy. So this is the equation for the Coulomb energy, also known as the electrical force energy. Okay, so the next thing I do here is I just plug numbers into this equation, and I get 37 mega electron volts. I'm going to divide that by 2 because I'm using the blue square as the estimate for the yellow curve. Okay, so 18 mega electron volts here at V sub A. So next I compute the potential energy of the particle at the distance r prime from the nucleus center. From this and the given kinetic energy of the alpha particle, I can estimate the distance it will travel. Okay, so that's what I've done here. This is the potential energy at this point here, where it's going to break. Well, it's actually going to break from the barrier here, but I want to compute L first. L here is this distance right here. Okay. So I'm just plugging numbers again, similar numbers into the Coulomb energy equation and solving for r prime. Okay, when I do that, I get r prime of 6.2 times 10 to the minus 14th. Okay, so that's this distance here from the center of the nucleus to here. Okay. Now what I really want is I want this distance here, L. Okay. And I can get that by subtracting r sub n from this r prime. And when I do that, I get 55 femtometers. That's 55 times 10 to the minus 15th. When divided by 2, that brings me back to my the barrier that I've created to estimate or approximate this yellow barrier. And again, the reason I'm doing that is because the mathematics for solving square barriers is really well known, and that's what I've shown you thus far. Okay, so finally all I got to do now is plug all the numbers that I have for the square barrier into this probability equation. Okay, so the energy of the alpha particle. Okay, this is the estimate of the potential of this blue box, the blue wall. Okay, and kappa here is estimated from this equation here. This comes from the Schrodinger wave equation. Okay, so this is the mass of the alpha particle. This is the difference in the energies between this energy and the energy of the alpha particle, and then dividing by Planck's constant. I get this value, so I'm going to plug that value in for kappa here, and I'm going to plug actually the L over 2, 28 femtometers, which is 2.8 times 10 to the minus 14th, in for this value here, and I get 1 over 1.6 times 10 to the 41. Okay, so this is the probability of the alpha particle escaping the uranium nucleus. Okay, so obviously this is a really, really small number. Far smaller than the probability of winning the lottery, but it is real. Every now and then, over millions of years, alpha particles escape the strong force of the nucleus. Okay, so let's move on. Okay, so again, the probability of a alpha particle tunneling through this barrier is 1 divided by this number. I can get the velocity of the alpha particle because I have its kinetic energy using this well-known formula. Okay, 1.4 times 10 to the 7th meters per second. I can figure out how long it takes to make a trip across the nucleus because I know its speed and I know the distance of the nucleus. Solve for time, and that's 1 times 10 to the minus 21 seconds. Okay, so the next thing I'm going to do is for the probability being close to 1 of this thing breaking out, okay, it's going to have to make this many number of attempts uh, of colliding against the nucleus wall. Okay. Okay, so that times the time it takes to go across the nucleus is this. So you multiply this together, and I get 1.6 times 10 to the 20th seconds. Okay, so in years, that's 5.1 times 10 to the 12th years. Okay, so half-life, about half of that, 2.5 or so, times 10 to the 12th years. So we know the half-life of uranium-235 is like 700 million years. Okay, so it's off by a factor of about 1,000, 10,000. But again, we used box potential to estimate this Coulomb potential, so I knew it would be off. But still, it just goes to show you it can be done, and it is a large number. Okay. If you're interested, here is the YouTube link for the quantum tunneling simulation that I showed you. So that's pretty amazing that we can use mathematics to estimate the probability of a spontaneous decay occurring. And as I mentioned before, it violates the classical perspective of conservation of energy. But in the quantum world, things are quite a bit different. Maybe in a future video, I'll show you why this isn't a violation of conservation of energy laws. Okay, so there is no absolutely precise model for the strong nuclear force, but we do have approximation models, and this is one of them. It's called the nuclear liquid drop model. And it consists of many energy terms. The strong nuclear force, this guy right here, okay? And that's called the volume term, okay? And it's equal to a constant, and they've actually computed these constants times the number of nucleons, okay? Okay, so that makes sense since there's a force between neutrons, protons, and protons, protons. So it increases with the number of protons and neutrons. Okay, so the next term is a negative correction to the first term since the number of nucleons on the outermost part of the sphere are not surrounded by other nucleons. Okay, so this term is proportional to the surface area of the sphere. Okay, this is just a constant. But how did we get a to the 2/3? Again, a is just the number of nucleons, but y to the 2/3. And this is how it goes. Okay, surface area for a sphere, 4 pi r squared, where r is equal to the radius of the nucleus times a to the 1/3. And I showed you where that came from previously. Okay, so if you plug this right into this, you get this, a constant times a to the 2/3, where the constant is 4 pi r radius, where r is the radius of the nucleus squared. Okay. And then of course, the coefficient a sub s includes this factor of c, and then another factor which basically explains experimental data. Okay, so that's where this term comes from. Okay, so this, well, let's go to the Coulomb term. Okay, this is a reduction in the binding energy, right? The strong nuclear force energy due to proton repulsion energy, right? Protons are positively charged, so they repel each other. And it is derived from this equation here, okay? So if we substitute the radius of the nucleus, okay, if we substitute this for this, and converting the rest to part of the constant a sub c, that's how we get this right here. Okay, so again, that's where the a to the 1/3 comes from. Z times z minus 1 is just z squared minus z. Okay, the rest of these are constants. That's the electron charge, or I'm sorry, the proton charge. Well, the proton charge and the electron charge are the same. This is a constant. So E squared over 4 pi epsilon naught, that's just factored into this a sub c term, but the a sub c term also includes a factor based on experimental results, which again fits this model to the data. Okay. All right, moving on. Okay, this is the asymmetry term. Okay. Okay, it's related to the fact that the nucleus prefers the number of neutrons equal to the number of protons, and I discussed this previously. This is quantum mechanical in nature. The last term is due to the pairing energy, okay, this guy right here, and reflects the fact that the nucleus is more stable for even nuclides, okay? So here are the estimates of all the constants, okay? So that's pretty remarkable. We even have an estimate for delta term here, okay? And that's here, A sub p, right? We have that here, divided by the number of nucleons to the 1/2 power. Okay, so I've presented this previously. Let me present it again. So this figure reveals that there are no stable nuclei with Z greater than 83, okay? Because of the increasingly larger Coulomb force wanting to tear the nucleus apart, okay? The strong nuclear force is still there, but now we're getting a higher ratio of protons, and that's why the nucleus becomes unstable. The heaviest known stable nucleus is bismuth, Bi. It's got 126 neutrons and 83 protons. So all nuclei with Z greater than 83 and A greater than 209 will eventually decay spontaneously into some combination of A nucleons with lighter masses. The repelling Coulomb force is just too strong to offset the short-acting nuclear force. Okay, for stable nuclei, the requirement is this: Z squared over A, right? So the number of protons squared divided by the number of nucleons, less than 47. Okay, so to the extent that this ratio is greater than 47, it will spontaneously fission. Okay, and we have not found a trace of such a nucleus. Okay, all right, so where does this equation come from? Okay, that's what I'm going to show you. Okay, so when an incident neutron strikes the target nucleus, as demonstrated previously, uranium-235, for example, the spherical shaped nucleus will deform. Okay, so it will go from looking like this to looking more like this. Okay, so let's assume that the stretch is to that of an ellipsoid. Okay, that's a three-dimensional ellipse of the same volume. Okay, now that makes sense. It's valid because nuclear matter behaves like an incompressible liquid, so the volume will not change. Okay, it turns out, and I'm not going to go into detail, you just have to trust me, that the surface energy term evolves as indicated below. Okay, so the surface energy term, this guy right here, becomes this for an ellipsoid, and the Coulomb energy term, this guy, evolves from this term, right, to this term, okay? Okay, so I added up the spherical terms, and I added up the ellipsoid terms, and I took the difference, and this is what I got. Clearly, if this energy difference is positive, then the spherical drop will be more tightly bound and consequently will be stable under a small external perturbation. For values for the constants previously given, the rule can be solved for algebraically from the above, and that yields this rule of, see the third term here, Z squared over A is less than 47.